It's a pleasure. It's a pleasure to present Rong Tang from Jilin University, and he'll talk about homotopy theory of postly algebras today. So there you go.
Thanks for Professor Doiko's introduction, and thanks. I should also thanks for Ivan's invitation. It is my great pleasure to give a talk on this wonderful seminar. This is a joint work with Andrey Lazarev from Lancaster and Yunhe from Changchun. My talk have four parts. First part, I will talk about some interesting construction about postally algebras. Second part, I will talk about homotopy theory about postally algebras. The third part, I will talk about the deformation theory of postally algebras. The final part, I will propose two natural questions about the homotopy, the cohomology and cohomology theory of postally algebras. Postally algebra is the algebra with a binary product. Uh, we usually call it the triangle map from G tensor G to G, such that the triangle map is a derivation of the Lie bracket and satisfy this equation. At first sight, this equation is a little complicated. We will return to this equation when we uh, have the subjacent Lie algebra, the subjacent Lie algebra of the pre-algebra. I should mention that postally algebra uh, is introduced by Valet in his study of Koszul duality of Koszul opera. Now, postally algebra structure have appeared in numerous mathematical and regularity structures. I list some interesting and important reference here. Given postally algebra, there is automatic Lie algebra structure, which is called the subjacent Lie algebra. The Lie bracket of the subjacent Lie bracket is defined to be that is the orange Lie bracket plus the commutator of the triangle of x and y. So use the subjacent Lie bracket, we can understand the second equation in the definition of postally algebra. This equation tells us that the subjacent Lie algebra action on the origin or action on the origin Lie algebra by the triangle map. So what is postally algebra? We can think about it is a vector space with two the algebra structures, and one is acting on another the algebra. If the Lie algebra structure in the postally algebra is trivial, so the postally algebra is pre-algebra. There are three very useful surveys about the pre-algebra and uh, its application in different directions. Now I will recall interested construction of postally algebra, which is come from the Lie algebra action on a commutative algebra. Here G is Lie algebra, A is commutative algebra. the algebra G action on the commutative algebra A, that is, we have the algebra homomorphism from G to the derivation, the algebra of A. Then there is a canonical postally algebra structure on A tensor G. The Lie bracket is very easy. It's just extend the Lie bracket from k linear to a linear. And the triangle is defined by this formula, that is A tensor X, triangle B tensor Y, is just use the X action on B. So this is the element belongs to A. So here is A multiplication on this element. In the application, we usually choose ABA to be A be the free commutative algebra generated by finite or infinite variables, and G be some interested the subalgebra of the derivation, the algebra of the commutative algebra. I should mention that this construction already appear in the integration and generalization of Rota-Baxter algebras, and it also appeared in the regularity structures. Now I will recall another construction of postally algebras, which is come from the magma algebra. A magma algebra is a vector space with an arbitrary binary product. So, Leibniz algebra, Pauli algebra, Jordan algebra, associative algebra, and so on, they are special cases of magma algebras. Then we extend the magma operation from the vector space V to the Freely algebra generated by the vector space V. Then the magma operation give a canonical postally algebra structure on the Freely algebra generated by the vector space V. Moreover, this construction is functorial. So we denote the forgot factor from the category of postally algebras to the category of magma algebras by G1. This forgot factor is just forgot the algebra structure in the postally algebras. So this forgot factor G1 has the left joint factor, we denote by F1. This left joint factor is just the above construction from the magma algebra to the postally algebra structure on the freely algebra generated by the vector space V. Now we denote the isomorphism class of planar Richard tree by PT. Then the left graphing operator on the planar Richard tree, which is defined by as follows: that given two planar Richard tree, tau and omega. Here, the planar Richard tree tau left graphs on omega equal to the sum of every node of omega, and each term is that here is that we left graph the planar root tree tau on each node of omega, and that is we add a new edge from the root of tau to every node of omega and a new edge on the right. Sorry, on the left. So this is why we call it this is reason why we call that is the left grafting operator. So the planar rooted tree with the left grafting operator is the free magma algebra generated by one element. So the forgot factor from the category of magma algebras to the category of sets has the left joint functor, which is the free magma algebra functor. Here we denote the left joint functor by F2. So F1 composition of F2 is the left joint functor from the functor of the forgot functor from the category of postally algebras to the category of sets. So the 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 functor F1 composition of F2 is the free postally algebra functor. So we use this method to give the concrete construction of free postally algebra. Here we consider the free algebra generated by the planar rooted tree. So we extend the left grafting operator from the planar rooted tree to the free the algebra generated by the planar rooted tree. Then the left grafting operator on the free algebra generated by the planar rooted tree is the free postally algebra generated by one element. Now I will also recall another postally algebra structure on free algebra. Here, the free algebra is just generated by two elements, x and y. Here, for element f belongs to the free algebra generated by x and y, we define a derivation denote f because uh, the derivation on the free algebra is just determined on the derivation on the generator. So we define the derivation denote f on x equal to 0 and denote f x on y equal to the Lie bracket of y and f. So we have a derivation on the free algebra generated by x and y. So for x and y be two elements in the free algebra generated by x and y, we define the binary product triangle as this formula, that is f triangle G equal to the derivation denote f action on G. So this triangle give a postally algebra structure on the free algebra generated by two elements x and y, and its subject algebra is the Ihara algebra. Now, this postally algebra structure and its subjacent algebra have already appeared in the application of multiple zeta values. There is the metal theorem in the regularity structures, which is given by Ivan Bullitt and his former student. They prove that Hopper algebra in multi-heads regularity structure is the universal developing algebra of a suitable postally algebra. Here, for more details about the postally algebra in the regularity structure, please see the Ivan and his students the paper algebras in regularity structure. Why Koszul algebra structure play an important role in the numerous mathematical and regularity structures? In my point of view, Koszul algebras are the algebraic structures underlying the Taylor type expansion of the solution of different kind of differential equations. First, if one want to study the Taylor expansion of the solution of differential equation on R, then one should use the free log of algebra and use the free log of algebra to define the multiple multi-indices Boucher series. If one want to study the Taylor expansion of the solution of differential equation on Rn, here n larger than 2, should use the free Pauli algebra and use the free Pauli algebra to define the Boucher series. One want to study the Taylor expansion of the solution of the differential equation on homogeneous space or Lie groups should use the free Koszul algebra and use the free Koszul algebra structure to define the Lie Boucher series. If one want to study the Taylor expansion of the solution of singular SPDE, should use the decorated tree Koszul algebra and use the decorated tree Koszul algebra to define the regularity Boucher series. In fact, the Koszul algebra appear in the regularity structure. It is the decorated tree Koszul algebra. Here I list some reference about the algebra structure related to the Taylor expansion of the solution of different kind of differential equations. Now we arrive at the second part of our talk, homotopy theory of Koszul algebras. Model categories provided a natural setting for homotopy theorem. Given a commutative square diagram of the following form, that is the composition of F and P equal to the composition of I and G. If the diagram is a map H from B to X, making the following two triangles commute, that is F equal to the combination of I and H, and G equal to the combination of H and P. Model category is a category with three distinguished classes of morphism. First class is called the weak equivalence. The second class is called the fibrations. The third class is called cofibrations. And each class close and compositions and contain identity maps and satisfy the following five axioms. At the first sight, the definition of model category is a little complicated, but it is the abstract view of the category of topological spaces. For more details about the model category and its application, I recommend the Quillen's book Homotopic Algebra. Here, I will recall a concrete example of model category. We denote the category of differential graded vector space over a field K by search of K. Then there is a model category structure on the category of differential graded vector space. Here, a cochain map MF from M to N is the weak equivalence. If F is quasi-isomorphism, A cochain map F is a fibration if F is the surjective cochain map. Finally, a cochain map F is a cofibration if F is the injective cochain map. Now I will recall the definition of differential graded postally algebras. A differential graded postally algebra over the field K is a differential graded vector space together with two graded bilinear product uh, product brace from G tensor G to G and a triangle from G tensor G such that the D is the derivation of the bracket and the D is also a derivation of the triangle. And the bracket is graded skew symmetric, and the bracket satisfies the graded Leibniz rule, and the triangle is the graded derivation of the bracket, and finally satisfies similar the similar condition in the definition of postally algebra. So we can find that a differential graded postally algebra over a field K is a postally algebraic object in the category of differential uh, graded vector space. We note that the forgot factor from the category of differential graded postally algebra to the category of differential graded vector space has a left joint functor, which is the free postally algebra functor from the category of the differential graded vector space to the category of differential graded postally algebras. By the transfer principle of model categories, one can obtain the model category structure on the category of differential graded postally algebras. Here, a homomorphism F from A to B is a weak equivalence if F is quasi-isomorphism. A homomorphism F from A to B is a fibration if F is a surjective homomorphism. And finally, a homomorphism F from A to B is a cofibration if F satisfies the left lifting property with respect to cyclic vibrations. So here we transfer use uh, use a free postally algebra functor and the forgot functor. This is the junction. With this junction to transfer the model category structure on the category of differential graded vector space to the category of differential graded postally algebras. We note that uh, uh, the postally algebra structure are the algebra structure over the postally operand, and the Koszul operand of the postally operand is the cotrialgebra, and the algebra structure over the cotrialgebra are the cumulative trialgebras. In our study of the homotopy theorem of differential graded postally algebra, we should use the dual of cumulative trialgebras, that is the cocommutative cotrialgebra. a graded cocommutative cotrialgebra is triple. C, capital delta and delta. Here C is the graded vector space. Capital delta and delta are two co-products on this graded vector space. Here C with the capital delta is the graded cocommutative coalgebra, and C with the delta is graded commutative coalgebra, and satisfy these two conditions. Now I will give a concrete example of cocommutative cotrialgebra. Here, given a graded vector space V, then there is a graded cocommutative cotrialgebra structure on SV tensor S bar V. Here, SV is the free commutative algebra generated by V, and S bar V is the non-unit co-free, the non-unit free commutative algebra generated by V. But here we will not use the algebra structure. We will use the coalgebra structure to define the capital delta and delta. Here, capital delta of x1 to xm tensor y1 to yn is just use the Koszul coproduct on each side of the tensor. That is, we use the Koszul coproduct to cut x1 to xm to like this, x sigma 1 to x sigma I, and x sigma I plus 1 to x sigma m. And similar, we use the Koszul coproduct to cut x1 to xm to y tau 1 to y tau j, and the last term is y tau j plus 1 and y tau n. And the delta of x1 to xm tensor y1 to yn is a little easier. That is, we fix the right hand side of the tensor. Just use the Koszul coproduct to cut x1 to xm to three tensors like this. We can prove that SV tensor S bar V with the capital delta and delta is a cofree conilpotent graded cocommutative cotrialgebra generated by the graded vector space V. A coderivation of a graded cocommutative cotrialgebra C is the graded linear map D from C to C such that D is the coderivation of capital delta, and D is also a coderivation of delta. Moreover, if the degree of D equal to 1 and D square equal to 0, and we call that C, the differential graded vector space C with the capital delta, and delta is a cocommutative cotrialgebra. Since SV tensor S bar V with the capital delta and delta is the cofree conilpotent cocommutative cotrialgebra generated by the graded vector space V, so the graded vector space of the coderivations on the cofree conilpotent cocommutative cotrialgebra is isomorphic to the graded vector space home from SV tensor S bar V to V. We will use this isomorphism to give the concrete construction of bar construction and co-bar construction. Here, given a differential graded postally algebra G, the bar construction of G we denote by B of G, which is a cofree, conilpotent, cocommutative, cotrialgebra generated by the graded vector space G shift 1 with the codifferential D1 plus D2. Here, D1 is induced by the internal differential D, and D2 is induced by the graded knit bracket and the graded triangle. Conversely, given a codifferential, conilpotent, cocommutative, cotrialgebra C, the cobar construction of C is denoted by omega of C, which is a free graded postally algebra generated by the graded vector space C shift minus 1 with the differential d1 plus d2. Here, d1 is induced by the internal differential d, and d2 is induced by the coproducts capital delta and delta. Moreover, the bar and the cobar construction are functorial, and then the cobar construction is the left joint functor of the bar construction between the category of codifferential, conilpotent, cocommutative, cotrialgebras and the category of differential graded postally algebras. Moreover, there is a model category structure on the codifferential, conilpotent, cocommutative, cotrialgebras, where a homomorphism F is the weak equivalence if the cobar construction of F is quasi-isomorphism of differential graded postally algebras. A homomorphism F is a cofibration if F is an injective homomorphism. Finally, a homomorphism F from the cocommutative cotrialgebra C to C prime is a fibration if F satisfies the right Liflin property with respect to the acyclic cofibrations. Moreover, the junction of cobar construction and bar construction has established a Quillen equivalence between the category of codifferential, conilpotent, cocommutative, cotrialgebras and the category of differential graded postally algebras. This theorem tells us that the homotopy theorem of differential graded postally algebras is the same as the homotopy theorem of codifferential, conilpotent, cocommutative, cotrialgebras. I should mention that for more details about the homotopy theory of DG algebra and homotopy algebras, please see the reference of Hanisch and Vallet. We note that the commutator of coderivations are still coderivations. So the graded vector space of the coderivations on the cofree, conilpotent, cocommutative, cotrialgebra generated by G shift 1 with the commutator is the graded knit algebra. We will use this graded knit algebra to give the abstract definition of postally infinity algebra. A postally infinity algebra structure on a Z-graded vector space G is a Magellan element M. Here M is a coderivation on the cofree, conilpotent, cocommutative, cotrialgebra generated by J shift 1, and such as that is the coderivation. The commutator of this coderivation m is the commutator of m and m equal to 0. That is m. This coderivation is the Magellan element of the coderivation, the algebra on the cofree, conilpotent, cocommutative, cotrialgebra generated by J-shift 1. And then the codifferential, cocommutative, cotrialgebra G of S of G shift 1 tensor S bar of G shift 1 with capital delta and with the coderivation M is called the bar construction of the postally inflating algebra G. Moreover, codifferential, conilpotent, cocommutative, cotrialgebra C is fibrate if only if it is isomorphic to the bar construction of postally inflating algebra G. Moreover, we analyze the coderivations on the cofree, conilpotent, cocommutative, cotrialgebra generated by J-shift 1 and use the concrete description of the coderivations. And then we give the concrete definition of postally inflating algebra. A postally inflating algebra is a Z-graded vector space G equipped with a family of linear maps MPQ from SP of G shift 1 tensor SQ of G shift 1 to G shift 1. Here, the degree of MPQ equal to 1 and P larger than 0, Q larger than 1, and satisfy the following identities. At the first sight, the definition of postally inflating algebra is a little complicated, but I should say this algebra structure is good enough because this algebra structure is stable under the homotopy. What is the meaning that this algebra structure is under the homotopy? If we have a postally inflating algebra structure on the graded differential graded vector space G, and here H is also a differential graded vector space. If H is a retraction of this of the differential graded vector space V, and then we can transfer the postally inflating algebra structure on G to its retraction H. So, in this point of view, postally inflating algebra structure is stable under the homotopy. Now, given a postally inflating algebra G, then there is a graded postally algebra structure on the cohomology space H star of G. Because we know that the cohomology space H star of G is a retraction of G. So by the homotopy transfer, there exists a minimal postally inflating algebra structure on H star of G. And moreover, given a differential graded postally algebra G, and then we can find that the differential graded postally algebra is a special case of postally inflating algebra. Here we define the M 01 equal to the differential G, and M02 equal to the graded Lie bracket, and M11 equal to the graded triangle, and other map in the postally inflating algebra structure MPQ, we define it to equal to 0. So this will give a postally inflating algebra structure. Now we arrive at the third part of our talk, deformation theory of postally algebras. Here, given a vector space V, we consider the graded vector space we denote by C no PL up star VV by this graded vector space, and the degree n part is defined by this vector space. Here, for f is the element of the degree n part, we write f equal to f0 to fn. Here, fi belongs to the home space from which iv tensor which n plus 1 minus iv to v. Moreover, for f and g be two homogeneous and G be two homogeneous element of the graded vector space, we define the cycle map as the following. At the first sight, the definition of the cycle map is a little complicated, but it comes from uh, the composition of coderivations on the cofree, conilpotent, cocommutative, cotrialgebras. So we can find that the graded commutator of the cycle map give a graded algebra structure on the graded vector space C no PL up star VV, and this graded algebra structure is very good because the Magellan element of this graded algebras are precisely the postally algebra structures on the vector space V. Now, given a postally algebra G, we denote the pi naught equal to the new bracket and pi 1 equal to the triangle. And we denote pi be the pair of pi naught and pi 1. So here pi is the Magellan element of the graded algebra H no PL up star GG. So we define inner derivation by pi as following. That is d lower pi of f, just the bracket of pi and f. Because pi is the Magellan element of the graded algebra structure on the C lower PL up star GG, then we can deduce that the inner derivation d lower pi is a differential on the graded algebra. So we obtain a differential graded algebra. And this differential graded algebra structure will control the deformation theory of the postally algebra G. Why? Because if we deform the Lie bracket from pi naught to pi naught plus pi naught prime and deform the pi 1 to pi 1 plus pi 1 prime, so that the pair pi naught prime, pi 1 prime is just the Magellan element of the uh, differential graded Lie algebra. So, given a postally algebra G, we denote the set of zero cochain space to be zero, and if the n larger than 1, we define the set of n cochain space to be the degree degree n minus one part of the differential graded linear algebra. And the co-boundary operator partial is just the differential below pi. The difference is that there is a sign here. So this co-chain complex is called the deformation cohomology complex of the post-linear algebra G. Moreover, one can use these cohomology groups to characterize the infinitesimal deformations, formal deformations, and extensions of post-linear algebras. Now, uh, I will propose two natural a problem about the cohomology theorem of post-linear algebras. In our previous work, we gave the concrete description of the cohomology theorem of post-linear algebras, but the co-chain space boundary operator is a little complicated. So it is a natural question or problem to that is that we can is that compute some cohomology group of low dimension post-linear algebras. Moreover, Mia have already uh, construct the abstraction class of algebra structure over Koszul operator. If the abstraction class is trivial, then the cohomology theory of the algebra structure is the derived functor of some home functor. So it's natural to consider the abstraction class of post-linear algebra. If the abstraction class is trivial, so uh, our construction of cohomology theory or post-linear algebra will also come from the derived functor of some home functor. And if the abstraction class is not trivial, so the cohomology theory or post-linear algebras will not come from the derived functor of home functor on the abelian category of the left modules of the developing universal developing algebra of post-linear algebras. I think I will stop here. Thanks for your attention and listening. Any questions or remarks?
Any questions from the audience? Okay. If not, then let's thank Rong again for his.
Sorry.
Okay, you have
I
one.
had a question. I was just muted by accident. Sorry.
Okay.
It's something rather simple, but I probably just missed it. What is the bar over the symmetric algebra mean? Because there were a lot of situations where you had SV tensor, SV bar, and I didn't catch what the bar meant.
Oh, thanks for your question. The S bar of V is just the non-unit, the non-unit free through symmetric algebra generated by V. So just the symmetric product from the one to two and infinity, not including the field K.
Okay. I see. Thank you.
No problem.
Any other questions or comments? Okay, probably not. So thanks again for your nice talk, and bye everybody. Bye-bye.
Thanks for what is, and thanks for Professor Doiko's the introduction.
It's my pleasure. Thank you
Yeah.
again.
Bye bye.
Bye.
Bye
Bye.
bye.
Thank you. Goodbye.
Bye.